Hello physics students. Today we're going to be analyzing the solenoid. Basically that's an electromagnet. Now I've already shown you a real solenoid in action, but what I want to do is remind you of what a solenoid is. So what I'm going to do is use my time machine to once again send you back in time to observe a real solenoid in action. So ready? Here we go. This is a solenoid. If I bring it closer to the camera, you could see that it's wire coiled around a copper core, and then I have these posts connected to the power supply. So I'm going to pass current into this coil of wire that's coiled into a cylindrical fashion. And what you're going to see is that then it has magnetic properties. So right now this is the north pole of the magnet, and when I turn this solenoid on, you see that it was attracted, the bar magnet is attracted to the solenoid. That means that this is right now acting just like the south pole of a magnet, right? So I bring a bar magnet, obviously there's attraction, so that means the solenoid acted momentarily while the current was on like a south pole over here attracting that north end. Now, if I switch the current around here in the solenoid, so I reverse its direction, so I go like this and like that, what happens is now this used to be a south pole, and you will see now that it is now like a north pole of a magnet. So essentially, this becomes this in the presence or when it has electric current going around through the coils of it. And also we could see evidence of that with paper clips. So right now the bar magnet picks up paper clips because of the magnetic properties and the fact that the paper clips have iron in them, so there's an attraction to the iron. Or it's more dramatic when I have a metal core here. Now you see this is not attracting any paper clips, but when I turn the current on, you see now I can attract the paper clips. And so I have, again, the current turned this into a magnet, which then can be shut off, right? So a little bit residual in this iron bar, but you see that I could turn the magnet on or turn it off by turning the current on in the solenoid or turning it off. So that's a solenoid, and once again, dramatic proof that the magnetic force is much stronger than the gravitational force. These are pulled down by the entire planet Earth, and one small solenoid overpowers the entire Earth because the Earth's pulling with force of gravity, the solenoid is pulling with this very strong magnetic force. Okay, so as you saw, turning on the current into the solenoid allowed the solenoid to pick up iron paper clips and also to interact with other magnets. And this shouldn't surprise you because, as we've learned throughout this topic, current creates magnetic field. But what we're seeing now is that when you spiral the wire into that helix pattern of a solenoid, it creates a magnetic field very similar to the magnetic field of a solenoid. The magnetic field of a bar magnet. Take a look at this image. This is the magnetic field around a bar magnet. Notice that the magnetic field comes out of the North Pole and goes into the South Pole. Also notice that there are just as many magnetic field lines coming out of the North Pole as there are going into the South Pole. And this is true of every single magnet in the universe. Interestingly, magnets always have equal strength poles. You can't also have just a North Pole or just a South Pole. All magnets, two poles, north-south, that are both equal in strength. Now take a look at this image of this solenoid. As you can see, it has that similar pattern of a magnetic field coming out of one end and going into the other. And if you took the time to count all the field lines, you'd have equal going out of one end as you have coming into the other end. So it has a similar pattern to the bar magnet. All right, so let's now take a moment to sketch that information. So here we have Ampere's law 3, the solenoid. Here's the magnetic field around a bar magnet. 1, 2, 3, 4, 5, 6, 7 lines coming out of north, and 1, 2, 3, 4, 5, 6, 7 going into south. Also note that the field lines can never cross. So that means you got to be real careful when you draw, like at the North Pole. Do not do this, just start making lines coming out like this and having them all sloppy here. You have to take the time to create a gap between all field lines, because at every point there's a unique magnetic field. And if you have lines crossing, then that means there's like two different fields at that point. So here it is, magnetic field around a bar magnet. Now here's the solenoid. We've got a cylinder around which we've wrapped a wire, and the current's coming in this side and out this side. This is coming in the front side of the solenoid and up the back side of the solenoid. And we have magnetic field lines. I drew 5 coming out this end and 5 going out into this end. So a similar kind of pattern. So I'll create a pause to allow you to copy these down. All right, so the next thing that we're going to do is we are now going to move on to actually calculating the magnetic field inside of a solenoid. Now, technically, we could use the Biot-Savart law, but the problem with that is the Biot-Savart law, because it works for any shape wire, but in the case of a solenoid, it's so difficult, humans can't really solve that. You can solve the magnetic field around and inside of a solenoid using the Biot-Savart law only with a computer. This image shows such a calculation, the net result of such a calculation. Now, some points about the solenoid magnetic field. As you can see, it passes through the solenoid, and in the region in the middle of the solenoid, you could see that the magnetic field is roughly constant. The way you can tell that is that the magnetic field lines are all equally spaced. When the field lines are far apart, that represents a weak magnetic field. When they're concentrated and close together, that means a strong magnetic field. But the magnetic field, the spacing is the same. That means a constant magnetic field inside of a solenoid. This is only true for what we call an ideal solenoid, and I'll explain in a moment. Now notice that the magnetic field near the ends the field lines start to spread out, and that means that the magnetic field gets weaker as you come out of the solenoid. So our analysis, too complicated to find the magnetic field at the ends. We're only going to be finding it in the middle region where it's roughly constant, and for that we're going to use Ampere's law. So that's what we're going to do now. Let's take a look. Now, I'm only analyzing what I call an ideal solenoid, or what's referred to as an ideal solenoid, and that means that the length of the solenoid is much, much greater than the radius or the diameter, however you want to look at it, of the cylinder you wrap the wire around. The other thing that I didn't put here is that the wires have to be pretty well packed. They can't be spiraling like this with big gaps between them. So in the solenoid I showed in the demonstration earlier with the time machine, you saw that the wires were really coiled together. That, is what we're talking about, packing the wires. So we have a certain current, a certain length to the solenoid that's much longer than the radius, and then we wrap the wire around a bunch of times, maybe 100, 200, 300, whatever, that we're going to denote by the variable capital N, how many times we wrap the wire around our solenoid. Another variable that's often used with solenoid is a lowercase n. It's like the turn density. If you take the total turns around the solenoid and divide by the length, then n will be the turns per meter, the density, the concentration. The more the coils are packed, the bigger n gets. All right, so as I said, we're going to analyze the solenoid with Ampere's law to determine the magnetic field. So here's a cross section. If I were to slice this in half down, a diameter, then what I would see, of course I only do it in my mind, if I really slice it in half, the solenoid won't work anymore. But what I would see is that if the electricity is coming in here and going into the board here, then these are wires where the current's going in, and then it spirals around the backside and comes out here. So that's why we have these, dots with the circles, as we mentioned, vectors coming out of the board, vectors going into the board, current right here of one of the wires. Now, how do we figure out the direction of the magnetic field? First of all, it's either going left or right inside the solenoid. We use this right-hand rule. We put our thumb in the direction of the current up here, and we see that the magnetic field will come into the solenoid like this, Or we could do it for the bottom wires, and I could put my thumb into the board, and I see that I also get the magnetic field caused by these wires going to the right. So the magnetic field's going this way. Now what I do is I have to think of an Amperian loop that'll allow me to calculate the magnetic field. I am not going to use a circle. That would not work. I use a rectangle like this. So has a certain width. This dimension doesn't matter how big it is. Again, and also the magnetic field out here is approximately 0 for an ideal solenoid. It would be 0. All right, so actually it would only be approximately 0. So there's my Amperian loop. Now what I'm going to do is use Ampere's law to figure out the magnetic field. So I write out Ampere's law here. And remember, as I've been saying, I have to create a pause here to allow you to copy this down. All right, so remember how I've been saying this over and over again. Every symbol here is critical. The circle, the vectors, and the dot. Let's suppose you left the dot off. Okay? What would happen is you would then have to integrate the magnetic field around here, and the direction of the magnetic field would not matter without a dot product. So there would be certainly an integral that would be non-zero across the top where we have magnetic field and ds, but the integral here would also be non-zero because we have b, we have ds, and it doesn't matter that they're not perpendicular. So yes, that would count. So the dot matters, right? Because that means now the magnetic field, not just the magnetic field along the Amperian loop, but the magnetic field that runs in the same direction as your integration. So here, B and ds are perpendicular, so these do not contribute to the integral that we have on the left side because of the dot product being 0. The only part of the integral that's not 0, well, there's no magnetic field, and here it's perpendicular, is along the top where B and ds align. So the dot product's not 0. So we just have B times W. That's all that survives at the integral. Now, what's the I enclosed over here? Well, if you look, in my picture I have 3 wires. So I would say like 3 times maybe 2 amps or whatever's going through, and that would be 6 amps coming out, going in, right? Well, okay, what about with symbols? What we would do is we would take the turns per meter times the meters would give us the number of wires that are inside our Amperian loop. As maybe a numerical example, let's suppose we had 100 turns in 2 meters, and then our Amperian loop was 0.1 meters. Then what we would have is 5 wires coming into there. So that's basically how these 2 terms work. And then we multiply by the current in each wire, gives a total current inside of our Amperian loop. And then all we have to do at this point is a little simplification by dividing the W away, and here it is right here. Or if we want to replace N per L, the turn density, then it's just mu0 N times I. Now, before we wrap it up, I do want to do a unit check. Remember, we always compare it to the units of mu0 I over 2 pi r. So we need mu0 amps per meter. Is that what we have here? Well, we have mu0. This is just a number with no units. This is in amps. And the length of the solenoid is in meters. So there we are. We have the right units. And this also, mu0, this is turns per meter. In other words, 1 over meter. And times amps. So the formulas have the right form. All right, so, I need to create a pause to give you a chance to copy this down. All right, so that's Ampere's law for a solenoid. A solenoid, sometimes called an electromagnet, is a spiral of wire. If you have a very long solenoid and a very relatively small radius or diameter, then you can use Ampere's law to determine the magnetic field inside the solenoid, which is constant throughout as long as you're not near the ends of the solenoid. So that's Ampere's law for a solenoid. I hope you enjoyed the demonstration from earlier in the year, and I hope you enjoyed the physics and the Ampere's law. I'll see you in the next physics video.